Okay, we're going to continue on here, doing some more reviewing of the chapters that we talked about this semester. Now that we were able to get through the door and get in here. So last time, I think we got through chapter 11, which was electron configuration and writing electron configurations. Any questions on any of those stuff that or chapters that we talked about previously? Okay, so then after 11, we went off to chapter 12, I believe. And chapter 12 really all about bonding, if I am not mistaken. Sounds good. So chapter 12 was really all about chemical bonding. So really in this chapter, we talked about different types of bonding. Really, again, there is ionic bonding, which is always between a metal and a non-metal. Remember that in ionic bonding, we really form ions here. So as we talked about, it is always usually the metal that will transfer those electrons to the non-metal. That creates a cation that is positively charged, bless you, and an anion that is negatively charged. And it is really that attraction, that electrostatic attraction, that basically holds those guys together. And again, the stronger the sort of positive negative charge, or the larger the charges, really the stronger the attraction is. So obviously something like sodium chloride is an example of that. Now, we also talked about covalent bonding. And in covalent bonding, that was between two nonmetals. And unlike ionic bonding, there is some sharing of electrons here. And really, the sharing of electrons can really be one of two things. They can be equal sharing of electrons. And that is what is referred to as a nonpolar covalent bond. Or just simply, most people just call it a nonpolar bond. And, that would be something like F2, for example. And we also can have a situation where it is unequal sharing of electrons. And that unequal sharing of electrons creates what's known as a polar covalent bond. And that is sometimes referred to as just a polar bond. The difference really between them, example, again, you could do something like HF. The difference between them is because the electrons are not being shared equally between the two atoms in that bond, we create partial charges. So for example, here, the fluorine would be partially negative, the hydrogen would be partially positive. We also can represent this with an arrow. And the arrow always points to the more negative side of the bond. And again, the part that kind of makes like a plus sign on the back end there is the more positive side of the bond. And again, that is another way that we could represent a polar bond. How do we really know when we're talking about bonding whether we end up with an ionic covalent bond? One of the main things that we look at is electronegativity. And as we talked about last time, electronegativity is the ability of an atom to bring electrons towards itself. And again, on the periodic table, we are increasing as we go that way there, up and to the right, with fluorine being the most electronegative, and we decrease as we go down. We could actually use, if you remember, the difference in electronegativity values. Remember, there are electronegativity values that run from 0 to 4, 4 being the most electronegative, and obviously 0 being the least. So if you values from that table, if you have anywhere from a difference of like 0 to 0.4, that's considered a nonpolar bond, or again, a nonpolar covalent bond. That would result in equal sharing of those electrons. Remember, if you have really a difference of 0 perfect, it's also referred to as a pure covalent bond. Again, it's still a nonpolar bond and equal sharing of electrons. Of their 0.4 to below 2, that is going to result in some type of covalent bond, which means that will result in a covalent bond. That will result in a polar covalent bond. Sorry, result in a polar bond, really, and that's going to result in unequal share. So that's going to create the sort of positive side, negative side to the bond. And typically speaking, anything above 2 will usually be ionic. Remember that you really don't need electronegativity values to help you determine that. As soon as you see it's a metal and a non-metal, that's pretty much all you need. Remember as well that there are some combinations of metals and non-metals, negativity difference of less than 2 that are ionic. They'll really just kind of go by metal, non-metal for ionic, and kind of use really electronegativity values to help you determine covalent bonding or non-polar. Remember as well, because electronegativity increases as you go up and to the right and down to the left, that if you are comparing 2 elements in the same row, you really don't need the values either. The one that is further to the right would be more electronegative, and it should result in a polar bond. Or if you're comparing 2 guys that are really in the same group as well, the one that is further up in the group should also be more electronegative and create a polar bond. So again, you don't always necessarily need values. You can make a pretty good placement of where they are on the table, and be correct in a lot of cases. Definitely if they're or same group, pretty much it's going to be a polar bond between those 2 things, because one's going to be higher up, be further to the right, and that will result in a polar bond. There are a couple of sticky places where you could have different elements that do sort of have the same electronegativity values. And remember, those are typically the ones that are not right diagonal to each other, but kind of like over as well, one. And they can sometimes kind of cancel out their contributions, like carbon and sulfur, for example, on the periodic table. They'll end up with kind of the same electronegativity value. But definitely if the 2 elements are the same, then for sure, excuse me, it will be a questions on that there. With that, we kind of moved into talking about actually how to draw a couple different types of Lewis structures. We talked about how to draw sort of Lewis structures for ionic compounds. And remember that when we draw them for ionic compounds, we use our Lewis symbols. So for example, if we had sodium, which would be 1s2, 2s2, 2p6, and 3s1 is electron configuration. And we reacted it with chlorine, which would be 1s2, 2s2, 2p6, 3s2, and 1, 2, 3, 4, 5, 3p5. What's going to happen here is, because sodium is group number 1, it has 1 valence electron. Chlorine is group number 7, which means it has 7 valence electrons. Remember that the number of valence electrons equals the group number, and it's the valence electrons which are the highest in energy, the ones that are bonding, really the only ones that are shown in Lewis structures. In this case, we would expect our sodium to transfer its electron over. Remember, at that point is when sodium will come up with a positive charge. And when the chlorine picks up that extra electron, that is when it will come up with a negative charge. And when we do draw for an ionic compounds, we do need to kind of put the charges in the picture, brackets or something like that, to indicate that they are not sharing electrons, that the electrons have been transferred. And remember, really the whole goal of all bonding is for everybody basically to achieve the same electron configuration as the noble gases, which is group 8. And when sodium loses that electron, which would be that one right there, it is left with 10, which means sodium becomes neon's configuration here. And when chlorine picks up that electron, it's going to go right into that spot, which means that the chlorine will then end up at argon's 18 configuration. And again, in the case of ionic bonding, that's pretty much the deal. The metals will lose electrons so that they can come back to noble gas configuration, and the non-metals will gain electrons go forward to the next noble gas configuration. Really, sort of the whole point of bonding in again, when you're drawing these guys, we do need to make sure that we do show the charges. And when we do the structures, by the way, when we do Lewis structures for covalent compounds, we will really follow a few different steps. The first step is you want to think about, well, really you want to kind of count up the total number of valence electrons. And when you count up the total number of valence electrons, remember that if it does have a charge, you also need to take that into consideration. So again, if something has a positive charge, you need to subtract from your total, so you end up with the right number of electrons. Somebody has a negative charge, you need to add to your total. Once you have that, you want the logical arrangement of the atoms. Remember that typically speaking, it is the least electronegative in the center atom. We never find fluorine or hydrogen in the center. Again, that is because hydrogen should only have 2 electrons. And if you put it in the center, it's probably going to have more. And fluorine being the most electronegative, it does not go in the center, so it should usually go on the outside. Once you have that logical arrangement, you want to make sure you just really make, whoops, if I could get that K, there we go. Make one covalent bond, or single bond, really, to the outside atoms. That will use up a certain number of electrons. So however many electrons are left over, the leftover electrons go on the outside atoms first. In pairs, so pairs of dots. And then if you still have leftover after you fill out the outside atoms, they go to the center atom in dots. At that point, once you put the dots on the central atom, you really should be out of electrons at that point. The last thing you really want to do is make sure the octet rule is met. Remember, the octet rule is the major rule there of bonding. Everybody will continue to make bonds until they have 8 valence electrons around them. Once you make sure the octet rule is met, you're done. If not, then you want to try to fix it by making double bonds or triple bonds if necessary. So remember that you do not want a double bond or triple bond kind of out of the gate. You kind of want to save it to fix any type of problem. And then you would obviously double bond and triple bond. Any questions on any of those sort of steps there? So we'll take a look here at one. So if we drew, say, our NF3, this here would have 5 for the nitrogen, which is group 5, 7 for each of the fluorine, and there's 3 of them. That means this picture again should have 26 valence electrons. Nitrogen being the least electronegative should go in the center. Fluorine should go around it. Again, one single bond from the center to each of the outside atoms. Each line represents 2 electrons. So that's 2, 4, 6. That then gives us 8, 10, 12 to put on the outside, 14, 16, 18, 20, 22, and 24. At this point, we filled up all the outside ones. We still have 2 to go. That would then go, if I could double dot there, in the center. At this point, everybody has 8 valence electrons around them. We've distributed all 26 electrons, and that's the proper way to do it. Remember that if you did have something with a charge, like we saw carbonate before, that would be 4 for the carbon. There's 3 oxygen, each is 16. Again, the -2 would mean we would add 2 electrons. That's going to give us 1824 in this case. Once again here, carbon would be in the center as it's further to the left than oxygen on the periodic table. So that would be CO and O and O. Again, making a single bond to each of these would be 6 electrons. We would fill up the rest of them there. That would be then 8, 10, 12, 14, 16, 18, 20, 22, and 24. At this point, everybody's good except for carbon. It is short 2 electrons. So this is the part where we would want to make a double bond to try to fix it. In this case, you could actually make a double bond at any of those guys. Remember that when we make a double bond or even a triple bond, we're actually bringing the electrons in to do it. We're not adding more electrons or adding more lines. When we do that, in this particular case, we would end up with a picture that looks something like this. Usually you put a little bracket around it with the charge because it's ionic. You also could draw what we talked about was referred to as resonance structures. By just really moving the double bond around. So that would be another structure we could have drew. And we could have drew another structure, again, resonance structure separated by these arrows. Where we double bonded there to the right in this case. The reason for these 3 structures are the double bond electrons are moving around. So the real structure is probably somewhere between all 3 of them. So if you're asked to draw the resonance structures, you could draw all 3 of those. Or if you just need to draw a Lewis structure, you could draw any one of the 3 and it would be perfectly fine. Any questions on drawing Lewis structures here? With this, we talked about geometry, valence shell, electron pair repulsion model. And remember that when we do geometry, there was 2 types of geometries that we talked about. The electron pair geometry, which describes how the electrons are arranged around the atom in 3-dimensional space, and also the molecular geometry, which is sometimes referred to as the shape, which is how the overall shape changes. Remember that the one major thing when we're doing geometry, double bond or a triple bond, it counts as 1 bond and 1 electron pair. So a double bond or a triple bond, when you're counting them, counts as 1 electron pair and 1 bond. So we talked about geometry here, and really the simplest geometry is a diatomic molecule, which is basically just 2 atoms together. No matter if it's single bonded, double bonded, triple bonded, the same element, different elements, the geometry of diatomic will always be linear because frankly, there's only 2 things, and the only way to connect 2 things is move atoms. And really the best way to do it is to count around the central atom on pairs. Around the central atom, remember that when you're doing about the central atom, and that will give you really the 2 names, the electron pair geometry will also give you the molecular geometry name. And there's also some bond angle is happening as well. So if you have electron pairs and 2 bonds, that is linear for both the electron pair geometry and also the molecular geometry has a bond angle of 180 degrees. You got 3 electron pairs and 3 bonds. That is what is known as trigonal planar, or some people call it triangular. Also trigonal planar for our molecular geometry, that's a bond angle of 120 degrees, kind of makes a triangle. This guy obviously is a kind of a straight line across. If you have 4 electron pairs and 4 bonds, the electron pair geometry is tetrahedral. And the molecular geometry is also tetrahedral. And has a bond angle of 109.5. It kind of has this sort of geometry looking type of thing. Now, in all these cases and above, there are no lone pairs on the central atom. Remember, lone pairs are non-bonding electrons or dots. So basically, if you draw your Lewis structure, you'll have no dots on your central atom. You will hit one of these geometries. And when you do have that situation, basically all you have is bonding electrons, which means that both the electron pair geometry name and the molecular geometry name will always be the same. So as you can see, they're both the same. It is only when you introduce non-bonding electrons that things get screwed up, because with non-bonding electrons, 2 things happen. You get really bad electron-electron repulsion when those non-bonding electrons get near bonding, and when non-bonding electrons get near non-bonding electrons. Secondly, you no longer have that extra atom there in the bond to kind of keep everything together. So it gives the molecule a little bit more room to spread out. So for example, I think we saw one with 3 electron pairs and only 2 bonds. Remember, it is not the electron pair geometry name that changes, but it's the molecular geometry name that actually changes. So something with 3 electron pairs is still trigonal planar. But because it has those non-bonding electrons, gives it a little bit more room to move around. This is the guy that we called in here angular. Again, sometimes people call it bent angular or just bent as well. It has a bond angle of less than 120 degrees. We also saw 4 electron pairs and 3 bonds. Once again, because it has 4 electron pairs, it's going to be tetrahedral for the electron pair geometry. But with the 3 bonds and that extra sort of opening there, it makes a shape that's known as trigonal pyramid. And it also has a bond angle less than 109.5. So it's kind of, you know, this guy is sort of like this angular type of thing. Our trigonal pyramid is sort of, you know, 3 bonds and some electrons coming up. It's sort of a pyramidal shape. Last one that you guys learned was 4 electron pairs and 2 bonds. Once again, 4 electron pairs, still going to be tetrahedral here. This one has like all the bad issues in terms of electrons, bonding near bonding, non-bonding near non-bonding, gives us what is known as bent or V-shaped. And that would be less than 109.5 degrees. And that is like water, which has that sort of arrangement to it. Any questions on geometry? Again, the best way to do it is just to know the table and count up the electron pairs correctly. Remember, 2 things people always screw up on geometry is it's always the central atom and double bonds and triple bonds, 1 electron pair and 1 bond. So for example, the 2 that we just drew over here, we would come to this guy. We would go to the central atom. It has 1, 2, 3, 4 electron pairs. And it has only 3 bonds, which would obviously be this guy, and this guy. So again, in terms of the electron pair geometry, because it has 4 electron pairs, it would be tetrahedral. But the molecular geometry in this case would be trigonal pyramid. Coming to our guy here, it has around the central atom, double bond counts as 1 electron pair, 2 electron pairs, 3 electron pairs. 1 electron pair for a single bond, 1 bond for the single bond, 1 bond for the single bond on that side. And once again, double bond going to count it for geometry as just 1 bond, which means it has 3 bonds. So the electron pair geometry for this guy would be trigonal planar. And because there's no dots around the central atom, it would also be the same name for the molecular geometry, which would also be trigonal planar. Questions on that there? Okay. Last thing we talked about here in the bonding chapter was molecular polarity. And remember, with molecular polarity, what we're talking about is not individual bonds, but the overall molecule. Is the overall molecule polar or non-polar? If the overall molecule is polar, have what is known as a dipole moment, which means kind of using that arrow, there will be a side of the molecule is more negative and a side that's more positive. If it's non-polar, dipole moment, which means that it is pretty much neutral. There's equal sharing of electrons over the molecule. There's no side that's negative or more positive. So the easiest one to do is diatomic molecules. That is the only one where both the bond polarity, which is where you use the difference in electronegativity, and the molecular polarity will be the same. And the reason for that is it's diatomic, which means it has one bond and one bond only, which means if that molecule, if that bond is polar, the molecule will be polar. And if that bond is nonpolar, the molecule will be nonpolar. When you get to 3 or more atoms, you have to look at 2 things. Are there polar bonds? And the molecular geometry. So for diatomic, very simple. This guy is a polar bond, which means this molecule would be polar. And for diatomic, this bond is a nonpolar bond, which means this molecule will also be nonpolar. But when we talk about these guys, there's really sort of a quick way we talked about that you can kind of figure out geometry or polarity, be correct in most cases, and that's with symmetrical geometries and unsymmetrical geometries. So symmetrical geometries, pretty much if you draw your Lewis structure and there are no dots on the central atom and all the outside atoms are the same, it will most likely be a nonpolar molecule. So the geometry for us here would be trigonal planar or tetrahedral. And this is, again, the molecular geometry we're talking about here. So if you have any of those, if you have either of these geometries and the outside atoms are different, most likely can then become a polar molecule. So remember, if you kind of change one of the atoms on the outside to something different, it goes from being nonpolar to polar. But if they are all the same, then it will be nonpolar. That leaves us pretty much a couple other geometries for you guys, which would be angular, bent or V-shaped, or trigonal pyramid. And what basically all these guys have in common are there are dots on the central atom. So when you draw the Lewis structure, you got those non-bonding electrons on the central atom. If all the outside atoms are the same, it most likely will be polar. So basically, you got dots, you got everybody on the outside the same. Polar, you have no dots, everybody on the outside different, going to be polar. That leaves really just linear. You have to think about, and linear is pretty simple. It's a straight line. So either everybody's going in opposite directions, which means they will cancel, or they're heading right at each other, which also means that they will cancel. But you could have one where all the sort of electronegativity is heading in the same direction, then it would be polar. But that one's kind of the easier one to determine. Any questions on molecular polarity there? All right, I think that in that chapter there. So I think that is the end of chapter 12. Then we went to the other big chapter there, which is backwards to chapter 5, which was So we talked about naming, about different types of naming. And really, we have one. Type 1 is a metal and a non-metal, which means it's ionic. And as we talked about with naming, whenever a metal's involved, it is the most important. And a type 1 metal basically has a fixed charge. From the periodic table, zinc, cadmium, or silver. They basically have a fixed charge, which means you just use the whole name of the metal. On metal, you drop the last part of the name there and you drop an IDE on it. So again, something like NaCl, there being sodium. So that would be that when we write the formula for an ionic compound, it should never have a charge, should always balance out to 0. And it does in this case because this is sodium and that is chloride, which has a minus equals 0. Just like if we had something like this, CaCl2. Ca is calcium, group 2, has a positive charge and fixed. This would be calcium chloride. Once again, no charge for the formula, but the cation here is a calcium charge. The anion here is not Cl2 minus, but it is actually 2 of them. So that is the proper anion there. And again, each of the chlorides there have -1, which gives you -2. And that balances out the +2 charge when you put it together. Shown type 1. Then we obviously went to type 2, which is pretty much similar. Type 2 also going to be an ionic compound, also going to be a metal and a non-metal. So once again here, it is our metal that's most important. This would be guys that have a variable positive charge. And those are going to be mainly our transition metals, are just to the right, underneath the staircase. Things like tin and lead and those guys, which are kind of under that staircase on the periodic table. Because it could have variable charges, we basically use the whole name of the metal, just like we did before. We then need to use Roman numerals. And remember that the Roman numeral basically indicates the charge on the metal, not how many you have. And then the non-metal is named the same way. You get the IDE at the end of it. So if you had FeBr2, iron is a transition metal, could have multiple charges. But we do know always what it's attached to. And this is bromine, which is group 7, has a -1 charge, and there's 2 of them, which means that this is an overall negative charge of -2. So the iron here has to be +2 to balance it out. And the name here would be iron, Roman numeral 2, because of the charge. And the non-metal is named just like normal. Doesn't matter. There's multiple non-metals there. It just becomes bromide. So this would be iron 2 bromide. And that is different than if you had FeBr3. Once again here, this iron could have a variable charge. There are 3 of these Br minuses. Gives us an overall -3, which means the iron here would be +3. And this would be iron Roman numeral 3 bromide in this case. Again, for the +3 charge that is there. And that is why we do need the Roman numerals, because in the first case, we were dealing with iron that had a +2 charge we're dealing with, while over here we are dealing with obviously the +3 charge. Any questions on that there? Then we talked about type 3 compound, and type 3 compound are non-metals together. And this do use prefixes. This is covalent bonding, this is sharing of electrons. This is where you want to use prefixes, nowhere else. So our prefixes, basically, we have mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, and deca for 10. Remember, there's just a couple of rules on this one. We do not use mono, so we do not use mono on first name, but okay on second. And we also get a couple of vowels that sometimes back up, so we get rid of the vowel from the prefix, like a O and O, an A and an O. So usually that prefix vowel is the one that sort of suffers there. So if you had something like N2O5, that is going to be not non-metal. We use the appropriate prefix. So that is 2. So we'll go with dinitrogen. Prefix here is 5, which would be penta. We will drop the A because the next word is oxide. So the second guy gets the IDE ending. The first guy, we use the whole name. And once again, we use the appropriate prefix if necessary on both of them. They're the easiest ones, as we talked about, because frankly, there's really nothing to balance in terms of charges or anything like that. You basically just got to choose the proper prefix there to do that. Any questions on that one? We then got into polyatomic ions. Remember, polyatomic ions are groups of nonmetals that have charges. So they are covalently bonded together, but overall they end up with a charge like the one we drew earlier, which was our carbonate. So this guy here is a polyatomic ion. It is actually held together by sharing of electrons, but overall it does have a charge. So it's considered an ion. Really, for the most part, as we talked about, polyatomic ions end in either 8 or ite. And usually the one that ends in 8 has the most oxygen. And the one with ite has the least oxygen. In groups that are related to each other, like NO3 minus, which is nitrate. NO2 minus is nitrite. There's also groups of 4 that are related to each other, like ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Remember that in a group of 4, the one with the most oxygen starts with per and ends with 8. The one with the next least most oxygen just ends in 8. The one with the least oxygen, or the next least oxygen, ends in ite. And the one that has the least oxygen in the group of 4 starts with hypo and ends in ite. So remember, there are other things as well. We sometimes can put a hydrogen in front of something and we call it like hydrogen carbonate or bicarbonate. There are some polyatomic ions that end in like IDE, like hydroxide, peroxide, azide, all those things. Yes, sir. There you go. It does. So, but a vast majority of them will end in 8 or ite. So a good way to remember these, as we talked about, if you still need to do some of that, is to maybe remember all the 8s, and the ites just have 1 oxygen less. The charge stays the same. Remember, the charges don't change and things that are related to each other, just the number of oxygens. Or you can remember all the ites and know the 8s just have 1 more oxygen and kind of move yourself up or down based off of that as well. When we're dealing with polyatomic ions, because they are pretty much, other than ammonium, I can make a plus there. other than the ammonium ion, which is not ammonia, but ammonium, pretty much most polyatomic ions are negative, which means they usually end up with a metal. So a lot of times we fall back to type 1 or type 2 sort of rules when we're dealing with polyatomic ions. So, if you had something like NaNO3, that is our polyatomic ion, which is nitrate, and this is our sodium. And it's really, again, the metal that's important there, because that's type 1, it would be sodium. And when we go to name the polyatomic ion, regardless of how many are, it's the name of it. So this would be sodium nitrate. Like FeNO3 to the 3. Once again, the iron here is our unknown. That gives us a -3, which means the iron here should be +3. And this would be iron Roman numeral 3. And once again, even though there are multiples of those guys, it is still nitrate at the end. So no prefixes or anything weird like that. That is basically how you do it. Any questions on polyatomic ions? Now, we talked about acids. And acids are really involved oxygen, right? It's basically how you determine how you name it. If it is no oxygen, the acid is hydro something ic acid, like HCl, would be hydrochloric acid. The negative guy would be the part that you fill in. If the answer is yes, there are oxygen, it most likely will have a polyatomic ion. And if your polyatomic ion ends in 8, your acid would be something ic acid, like HNO3. NO3 is nitrate, ATE. This becomes nitric acid. And if your answer is yes, and your polyatomic ion ends in ite, your acid will be OUS acid, like HNO2. NO2 is nitrite. This would be nitrous acid. Yeah. Remember that for all, the cation is H plus. There it is. The cation is always H plus, and the anion is obviously whatever negative guy. It is treated kind of like an ionic compound, so we do want to balance it out to 0. So once again, you should never have a charge on your formula of an acid. It should equal 0. And if you have a polyatomic ion there that has like a little prefix or something in there, like HClO4, that is perchlorate. That becomes perchloric acid. Again, we keep the per in it as well. Any questions on naming there? Okay. The next place, I think after that, was to chapter 8. And in chapter 8, we talked about moles and so forth. So we talked about a couple of different sort of really important conversions, and that is Avogadro's number, which is 6.022 times 10 to the 23. These could be particles, these could be atoms, these could be molecules, and that all equals 1 mole. And we use this as a conversion factor, really in our case, to kind of go between these units, to go between atoms or molecules to moles. You would use, again, Avogadro's number to do so. The other important sort of conversion that we saw in that chapter was molar mass. And molar mass can be basically gotten from the periodic table. We can use it as the number below the symbol. That is also the atomic mass, really, which we also talked about in that chapter, how to calculate atomic mass. But in addition to atomic mass, which is usually AMU per atom, molar mass is grams per mole. So the atomic mass are basically numerically equal to each other. That means from the periodic table, we can pull off something like there's 1.008 grams for every mole of hydrogen, and the molar mass of hydrogen would be 1.008 grams per mole. If we had a molecule, we just add up the parts. So 2 times 1.008 plus 16 gives us 18.02 grams per mole. Remember, we use this really as a conversion factor, and a really important one to go from grams to moles, or moles back to grams. We could use a molar mass like this as really dimensional analysis conversion factors, 18.02 grams per mole, or you could put the moles up on top and 18.02 grams up on the bottom. Which first case you would be multiplying, second case you'd be dividing by the number. And if you have grams, you would go opposites of each other and divide by the molar mass so that the grams cancel and you end up with moles. Or if you're starting with moles and you want grams, you would multiply by the molar mass, where again, the moles would cancel and that would leave you grams in that case. So those are really important. Molar mass a lot. Typically speaking, we go 4 significant figures off the periodic table when we do use molar mass. Let's see here. The other thing that I think was in here was we also talked about percent composition by mass. And really, if you had a formula like water, you could get the molar mass of it. And you basically could figure out the percentage of each element that's present. So the percentage of hydrogen would be 2 times 1.008 divided by the molar mass of the entire thing times 100%. You could also do the same thing for oxygen. It would be 16 grams per mole, which would be oxygen, since there's just one in the formula, and also be divided by the entire mass, molar mass of the compound times 100%. And that would give you your percentage of oxygen. Obviously, when you get those percentages, they should add up to 100% if you have everything. A lot of times we see this occur when we talk about empirical formulas, which we also did in this chapter, and molecular formulas. So empirical formulas are the simplest whole number ratio of what elements are present. While the molecular formula really tells you exactly how many of each element is present. So for example, if we had C2H4 as our, try that this way, C2H4 as our molecular formula, we could look at that and we could see that in this formula here, there are 2 carbons for every 4 hydrogens. That's the same as a 1-to-2 relationship, which means we could just simply divide everybody by 2 there and end up with CH2, which would be our empirical formula in this particular case. Now, some molecular formulas, empirical formulas are the same. So if you had something like water, that basically is 2 hydrogens for every 1 oxygen. You pretty much can't get any more reduced than that and still have a whole number. More importantly, in this chapter, we also talked about how to calculate these things from values. So to calculate the empirical formula, the first thing you want to do is convert the percentages into grams if you are given basically the percent by composition by mass. Remember that if you are given the percent composition by mass, you could assume 100 grams. And that basically will keep in terms of their numbers. You then want to convert the grams to moles. using the molar mass from the periodic table. You will now have moles of all elements. You want to then divide by the smallest number of moles. So again, for example, if I had 2 moles of A and 4 moles of B at this point, here we would divide everybody by 2, which is the smallest number of moles. That would give us basically 1 mole for A and 2 moles for B, which means our empirical formula here would be AB2. Now, if you do get to this point and you say had something different like 2 moles of A and 5 moles of B, here we would divide by 2. That would give us 1 and 2.5. That would give us an empirical formula AB 2.5. Remember that these need to be whole numbers. This is too far to round when you got 0.5, 0.33, and things of that nature. So you need to multiply everybody by a common number to get to a whole number. So in this case, we took 2.5 and times it by 2, you get 5. We want to multiply not just that guy, but everybody by that factor of 2. That would give us A2B5 as our proper empirical formula. So remember, when you're calculating empirical formula, especially textbook type problems, exam type problems, you pretty much need to be super close to that whole number in order to round. But if you're definitely not really right on it, you need to find a factor to multiply everybody by. Any questions on that there? Now, with this, we also talked about how to calculate the molecular formula. And pretty much you need 3 things to calculate the molecular formula. You need the empirical formula. So either you need to calculate it yourself or it's given to you. You need the molar mass of the empirical formula. Again, either given to you or calculated. And lastly, you need the molar mass of the compound, or the approximate molar mass of the compound. That is usually given to you in a textbook problem. So that is usually given to you in the problem. Somewhere they'll say the approximate molar mass of the compound is this, or molar mass of the compound is that. So what you do is you basically take the molar mass of the compound, or the approximate, and you divide it by the molar mass of the empirical formula, and that will give you a number. And that number you multiply the empirical formula by, and that will give you your molecular formula. So for example, let's just say we did that and we got a number of 4, and we took our made up one from the previous page there, and this was our empirical formula. We would then multiply everybody here by 4, and that would give us A8 and B40 as our molecular formula. So that's usually what you want to do. Really, the only place where it's maybe safe to do a little bit of rounding is if this guy's not a whole number. It's probably safe to round out probably to a whole number, because it should be pretty much a whole number multiple there. So that's probably a safe spot to round. Question on empirical formulas, molecular formulas, any of those things there. Okay, so I think at this point we will lay it up, I think, here now.